We can just go up. I didn't see what was
Good evening, everybody. Welcome to the Gulf of Maine Research Institute. My name is Jonathan Lavery. I'm the Chief Community Officer here at GMRI, which means I run our community department, which is one of our three departments. Most of you have been here before, right? A lot of you have been here before, so you know that the Gulf of Maine Research Institute is a marine research lab here in Portland. We study the Gulf of Maine, try to understand what's going on out in the Gulf of Maine. We also educate our state's children in science and try to get them engaged and interested in science and build a public out there that understands and appreciates science and the role it can play in our society and help us make good decisions about our natural resources. And then the program I run, our community department, we work with fishing communities around the Gulf of Maine as they adapt to changes in regulations and markets and ecosystems. So we try to get people engaged in the management process of fisheries and get the public interested in buying good, sustainable Gulf of Maine seafood and these sorts of things. Before I introduce our speaker, I also just want to thank our sponsors, the Morton Kelly Charitable Foundation and FishFed is the tenant here in the lab, and they generously support this program and help us bring lectures every year, 2 series every year to the public and make it available for free, which is really, really great. Our series this year is kicking off this part of the year. It's about ocean exploration, and we're highlighting a number of people who will explore the ocean, different aspects of the ocean, using different technologies and different approaches. And so kicking it off is Larry Mayer, and it's a huge honor to have him here. He gave a talk here today to staff, and it was just so great to see the technology he uses and the things, the way he explores and the things he's discovering about the ocean. Larry is the director of the School of Marine Science and Ocean Engineering at the University of New Hampshire and the Center for Coastal and Ocean Mapping. After being selected as an astronaut candidate finalist, find out a little bit more about that.
A long time ago.
NASA's first class admission specialist who went on to study oceanography at the University of Rhode Island. He's held posts at Dalhousie University, University of New Brunswick, and became in 2000 the founding director of the Center for Coastal and Ocean Mapping at the University of New Hampshire, and the co-director of a joint hydrological center between NOAA, the National Oceanographic and Atmospheric Administration, and the University of New Hampshire. Larry served on lots of panels and commissions and has lent his expertise in many different ways, including the President's Panel on Ocean Exploration, National Science Foundation's Advisory Committee for Geosciences, and has chaired the National Academy of Science Committee on the National Needs for Coastal Mapping. I could go on and on, but it's a real thrill. Looking forward to this.
It is a real pleasure to be here. I've been up here a few times, and I was actually at meetings upstairs, but twice a day I hear this room fill up with children and hear the rod. It was a wonderful thing, and I just thought this was a lovely venue. As John said, what I do is explore the ocean, but I do it through mapping. And what I want to do tonight is kind of just share some of that with you, and maybe explain how I got there and what we do, and maybe hopefully share some of the excitement. And I'm going to start way back and what got me involved. That's not the picture. That's the picture. And I was inspired back in the 1960s by Jacques Cousteau. And it's so important to have people like this who have a public image and present the stuff we do in a way that really enthralls the public. And today we have folks like Bob Ballard, and it's wonderful. We need to keep that kind of tradition up. But what really sucked me in was the images on National Geographic, the images they would show, these spectacular pictures of things I still have no idea what they are. They're just beautiful. And I just loved it. I said, I need to understand that. And I see all these amazing things. I just wanted to be an ocean explorer. And again, I have no idea what it is. Maybe there's some people here who do, but it was just absolutely enthralling. And not only marine life, but spectacular history under the ocean, wrecks that just absolutely amazed me. And even things that I do know about today, because I'm actually a geologist, geophysicist by training. And so this is actually blisters, volcanic blisters that form near ridge crests on the water. So it was always the images, always the images. So I said, boy, if I want to explore the ocean, I've got to image the ocean. And then I started to learn about it. How do I image it? What would it take to image it? Well, it's easy to image the Earth. We can go now to Google Earth, and we can zoom in anywhere. A couple of weeks ago, I was at a big meeting in Monaco, and I could just boom and zoom, go to Google Earth, zoom right into Monaco. I can go even closer and closer. It's from a satellite. It's just remarkable what we can see. And I could probably go even closer, but in Monaco, it would probably be X-rated if I zoomed in closer to some of those yachts. So it's just really easy now these days to image the brown part and the green part of the Earth. But what about that other part, the blue part of the Earth? And Arthur C. Clarke has this wonderful saying, how inappropriate to call this planet Earth when clearly it's ocean. 3/4 of the planet is the blue part. But what happens if I try that same technique, if I go zooming in from the satellite and I zoom in there? That's all I see. I just get the surface of the ocean because light just doesn't travel very well in the ocean. The ocean isn't transparent for light. And that's a big frustration. I get all this water, very bothersome to me. I want to explore the seafloor. And so we have to look for another way to do it. And what we have to do is somehow penetrate that water. And we're fortunate we have the technology to do it. We have things like remotely operated vehicles that we can send down with high resolution cameras that collected those beautiful images you saw. We can do even now autonomous vehicles. They don't even have to be attached by a wire. Robotic vehicles that go down with cameras like that, and we can explore it. But again, because of the problem that light doesn't travel very far in the ocean, when we take a picture, one of those high resolution pictures, all we get in a field of view is about, well, meters per second, but I'll translate 3 feet by 3 feet or so. And that's it. That's all we can see in a single picture. So I sat down and I said, well, if I want to image the whole ocean seafloor with that kind of spectacular imagery, how many pictures would it take? I can't say that. Big number. And then I know how long it would take me to get the vehicle down to the bottom, how long the pictures are instantaneous, basically. Not to take a lot of money, but I got to go up and down lots of times. How long would it take me to take that many pictures? About 10 minutes. I might be off by an order, actually, but it really doesn't matter. I'm a patient person, but well, actually, I might agree with that. But I can't wait that long. So this imagery is spectacular, but we need to find another approach. And that approach has to be sound, because it's sound that travels so long in the ocean. And so what I'm going to talk most about today is how we use sound to map the ocean. But let me turn now and ask why. Why? Who cares? I got excited about it, but is it important? Yeah, to me it is, because it's a fundamental tool for exploration. There's so much we don't know about the ocean. I'll make that point at the end. I'll show you how much we have actually accurately mapped. It's remarkably little. But we have actually some real pragmatic reasons to map the ocean. And this is something, until I got in this business, I had no idea that in this day of airlines and everything, still to this day, 98% by volume of the imports that come into the US come by ships. You're not going to fly all the stuff we use in on planes, it comes in on ships. And so safety and navigation is critical for our economy. It's critical for safety. And if something like that happens to a ship, it's a very, very bad day for the economy. It's a bad day for the environment. It's a bad day for the captain. And so the way we prevent this from happening is that we have to map the seafloor for safety and navigation. That's one of the biggest drivers of mapping. This is a remarkable picture because as the climate is warming and the glaciers are receding, tourists, ecotourism, tourist ships up in Alaska want to get closer and closer and closer to the glaciers. This picture was taken from NOAA, this National Oceanographic Atmospheric Agency. They're the ones responsible for making the charts we use. from their survey vessel, which was out here. That ship is in water that had never been surveyed before. Well, maybe Captain Cook went by there and surveyed it once, but no information about it. They were surveying out here to take that picture of the ship inside there. Sometimes it leads to things like that. And again, a bad day for the captain, a bad day for the environment, sometimes a very bad day for the passengers too. And so we're driven particularly by pressures like that. This is an out-of-date picture. This is the picture we show the congressmen and the senators about the size of some of the ships we have now. That's to scale with respect to the Capitol. And now they're bigger. They're bigger than that. And so that's the problem. Those ships have a very, very deep drag. And so we really need to understand what's beneath them. We obviously have issues with understanding what's on the seafloor, because one of the triad of our national defense is the underwater defense system. We have vessels that have to navigate underwater. Clearly, they have a need to understand what's down there. We have issues with national sovereignty. Big words. It's not a big word, it's a word I just can't say. Sovereignty. Thank you. And I'll talk about that in a minute, because I'll show you that mapping is a critical aspect of extending our sovereign rights over resources through something called the Law of the Sea Treaty. Every one of the fiber optic cables that gets laid on the seafloor needs to be mapped. It's of course the first thing that the oil companies and exploration companies do for exploitation, for exploration, but at the same time, it's the first thing that the resource agencies to protect those resources do, to create sanctuaries and preservation zones. They have to be mapped before they do that. So it works on both sides. Fisheries habitat, understanding fisheries habitat is a mapping issue. And it's critical to understand the depths, the bathymetry we call it, to understand the circulation of the ocean, which is involved with distribution of heat, climate change, and if we're going to predict where tsunamis would actually do danger, it has very much to do with the depth of the seafloor. The tsunami out in the deep ocean is a very, very small wave. It's only when it runs up near the coast, if the seafloor has a certain shape, that it rises to a very, very large and dangerous wave. So we need to understand the coast, the shape of the seafloor for that. So all these real reasons to map the seafloor. And I'm not going to show that picture. That wasn't working. That was actually a model of what happened in the Indian Ocean tsunami. So let me take a second and talk about how we map the seafloor, because people have been mapping the seafloor for a really long time. This is a statue that was found in the tomb of an Egyptian tomb, 2000 BC was dated. And right up here is the Egyptian ocean mapper. And what he's got is, I don't know if it's a rock or a hunk of lead at the end of the rope. And he would lower that down on the boat to measure how deep it was. So that's 4,000 years ago. They were mapping. The next picture I was able to find, to jump something like 3,500 years later, this is a wood carving from the Thames River. And what are they doing? The same technique. Hunk of lead at the end of the rope, something we call the lead line. And in shallow water, it's actually pretty accurate. But in deep water, you can imagine thousands and thousands of feet of rope. You know, did I hit the bottom? Did I hit the bottom? Well, they used to. Let me show the next picture. So what I want to do now is jump 500 years and show you how the technology changed. If I look 500 years ahead, what are they doing? Exactly the same thing, 1940. So for 4,000 years, there's basically been no change in technology. That's a slight exaggeration, because what they did in the old days, at the bottom of that hunk of lead, there was a hollow, and they used to put tallow on the bottom, and fat of some sort. And so when they would lower and lower, they weren't sure if they hit the bottom, they would actually be able to see it had a little bit of the sand or grains that were on the bottom. They also gave them an idea what was on the bottom. So tracing the history of this, I only found 2 innovations over 4,000 years. They originally started by using hemp, and somewhere in history that changed to piano wire and stretch, it was easier to make longer. So that was the one innovation. And the other innovation is that this tallow, somewhere, and I haven't been able to track when, changed to peanut butter. So the 2 great innovations of 4,000 years of ocean mapping: piano wire to hemp to piano wire, and tallow to peanut butter. That was it. And that was really until about the time of the Second World War. And during that, echosounds were developed. And really, it was happening in between the wars of development, but really the second one was the impetus to really rapidly develop echo sound. This was mostly for undersea warfare, for detecting submarines and navigating vessels. And with an echo sounder, as I said, sound, unlike light, travels very, very nicely in the ocean. And so you set off some sound. You can take two pots and bang them together, or use what we use is something called a transducer. It's a ceramic that if you apply a voltage to, it actually vibrates, and that makes the sound. And it sends out a sound wave, and it travels and travels and travels until it hits something hard or something with different properties, and then it'll bounce off. And if you know how fast the sound travels in seawater, we do know that, you can measure that. You just take how long it travels and divide by 2, and then you can figure out the speed, you can figure out how deep it is. And it's just like when you sit across a canyon wall and you yell and you hear the echo back, and you know how fast sound travels in the air. You divide that by 2, you can figure out how far the wall. When you hear the difference between lightning and thunder, you see the flash of lightning if you count. When you hear the thunder, they happen at the same time, but the light is traveling very fast, and the thunder is traveling much more slowly. And so if you know the speed of sound in the air, you can figure out how far away the storm is. So it's the same principle, but this echo sounder that they developed is something we call a single beam echo sounder, and I don't know how well we're going to be able to demonstrate that. When that sound goes out, it spreads in a big cone on the seafloor. And it's something like, I don't know how bright this will be. Yeah, okay, so I have this little tiny light here, but you can see it's a big, because it's spreading out like that. And so that creates a little problem. That cone of sound goes out, and it insonifies a whole area. And that area is something like how deep it is. So if it's 10,000 feet deep, that circle is going to be 10,000 feet wide, and yet you only get one bounce back. And you don't know where that bounce back came from in that circle. You can only assume that it comes from directly below the vessel. So you get this kind of blurry picture of the bottom, averaged over something like the water depth, 10,000 feet, if you're in that kind of water depth. And from that kind of blurry picture, we get this kind of two-dimensional record. We see it's going up and down, but it's really this kind of smoothed out version. And that was a tremendous innovation. Imagine a sound. Anybody know how fast sound travels through sea level? Wait, I don't know what it is in feet. 1,500 meters per second, so about 5,000 feet per second. Okay, so so it's a lot faster than lowering the rope, and it's a lot more accurate. But again, it's this blurry picture. But it was from that, from lead lines and from these single beam echo sounders, that most of the charts, the navigation charts that you see today, were made from. So this is the navigation chart has these are selected soundings. To show you this is Portsmouth Harbor where we live. Right on board. And then these will call contours. These are lines somebody uses their imagination and kind of connects the dots and says that's a line that people get, contour line. And so most of the charts we've seen came from those single beam echo sounders and from lead line information. Still to this day, about 50% of the information on the charts come from lead line measurements. It's really quite remarkable. That's shallow water. We've had an equivalent process in deep water, and that's really more from the oceanographic institutions who, for years since the Second World War, have all had these echo sounders on their ships. And here's where I went to school in Scripps, Institution of Oceanography here in San Diego. And all the ships coming out of Scripps, each one with a single beam echo sounder, right? So each one getting this kind of blurry track. And then somebody again using their imagination and connects the dots and draws contour map. And until 1999, which to me is not that long ago, some of you were born, but this was the very best map we had of Southern California. That was it, of what the seafloor of Southern California looked like. And I'll show you how it changed. And then something happened, and this happened as I get older. It used to be just 5 years ago, 10 years ago, now it's about 30 years ago. A real innovation. And we went from that single beam echo sound to that one big broad beam of sound to something we call a multi-beam echo sound. And instead of sending out that wide cone of sound, the one that kind of gives you that big broad spot like that, what it sent out was using a bunch of tricks from electronics, something we call beamforming, was a beam of sound that's just like a laser beam, just really, really narrow. But it didn't send out one, it sent out hundreds of them simultaneously across a wide swath. So every one of those yellow dots is one really highly accurate depth measurement that spreads across the seafloor with a width that's something like 4 times the water depth. So if you're 10,000 feet of water, you now have 40,000 feet. This is what we're going to be looking at. A lot of area covered on the seafloor all at once with lots of individual depth measurements. It really, really radically changes the way we see the seafloor. You can imagine get this one blurry measurement, suddenly hundreds and hundreds of measurements all at once across a wide swath. And so it changed it from that one single measurement to now hundreds. Each one of these yellow dots, an individual measurement over a wide area. Suddenly we just had a totally different view of the seafloor. And we went from this chart of Portsmouth Harbor to now looking at Portsmouth Harbor like that, where we see all the details. And this is just depth. This is color coded by depth. So, but we can see, even though it's only telling us depths, you can tell that this is a sandway field and there are rocks here. You can actually see what it is, too. It's really quite remarkable. We have better ways, even now, looking at the nature of the sound coming back to tell what the material is on top of that. So it's just revolutionized the way we look at the seafloor. And if we look at the Southern California area, we said that 1999 was the best map we had of the seafloor of Southern California. Our colleague and I spent less than 2 months with those multi-beam sonars in that area, and we turned that into that. And just as it says, it's just a radically new perspective, providing all kinds of new insights into the processes, what's going on. And we just never were able to see that stuff before. So it really, truly revolutionized our way of looking at the seafloor. And this has led to all kinds of new applications. I mentioned earlier, this one about sovereignty or sovereign rights. And that's something called the Law of the Sea Treaty. It's this very thick book that's really a constitution for the ocean. It's actually an amazing document, a whole set of laws for how the ocean should be maintained and how nations interact in terms of navigation, resource exploitation, exploration, everything. Sadly, the U.S. is one of about 9 countries, 165 nations have ratified this treaty. The U.S. is with North Korea, Libya, Syria. There are about 9 of us who haven't done this. And so, but the good part of it is that despite the fact that we actually haven't signed on the bottom line, the U.S. treats it as what's called international customary law, and we obey all its tenets. And we are going through the process of using the rules of the Law of the Sea Treaty to establish our sovereign rights over resources. Because one of the things it does is one little article, just 670 words, that as a geologist, when I think of the continental shelf, I think of this kind of flat part that comes from the beach before it gets a little steeper. Well, this legally defines something they call a continental shelf. I don't know why they use the same word, it's confusing. But it basically says if you follow a bunch of rules that have to do with the shape of the seafloor, and you can extend your sovereign rights over the resources of the seafloor and the subsurface, oil and gas, really, way beyond what every country is entitled to, which is 200 nautical miles. And for the U.S., the estimate is that in our extended continental shelf that we would get rights to through this process is something like $13 trillion worth of resources. But not only can you extend your rights to exploit those resources, you also extend your right to protect those resources. And for places like the Arctic, where the U.S. has a tremendously large extended continental shelf, if we didn't establish our claim to that area, it would then be open to us to exploit. So we can actually establish a claim to protect it from the exploitation, at least, and if it's going to be exploited, control the way that it's done. So it's a tremendously important process. Since 2003, our lab has been responsible for doing that mapping in all the places where the U.S. has a potential extended continental shelf, the Atlantic, the Gulf of Mexico, Alaska, Bering Sea, Marianas, because of Guam, Johnson Atoll, here Kingdom, Palmyra, U.S. possessions, and so on. But the biggest place that I mentioned is the Arctic. We've had 8 cruises already, and we're leaving in September for our 9th cruise. Again, they establish how far our extended continental shelf goes out there. And every time we've gone out to do this with new multi-beam sonar systems, these are all areas that have never been mapped before. We go from, that was the best view, this happens to be the Gulf of Alaska, the best view we had of the seafloor before, what it looks like in reality. And again, a radical difference. And from a law of the sea perspective, it's a huge difference because if we had to use this information key aspect in the law of the sea treaty is what they call the foot of the continent, the foot of the slope, where there's a change of slope. You can hardly see it here, it would be somewhere in here. But here, you can see it very clearly, and it comes way out. And each one of the things that comes out, and you're allowed to connect the dots with 60 nautical mile straight line. So the U.S. extended the continental shelf was way, way out here with the new data, and with the old data, it would be much, much less. So it's very, very important. And this is the truth. The other data was just as blurry as what it is, and that's what it really looks like. As I said, we have to do this in the Arctic. The areas that we work in are very far north. They're ice covered, even with the diminishing ice. I believe I've been going up there for 10 years now, and every year we see the ice diminish. But we still need to use big icebreakers, and we're fortunate that we have at least one, and hopefully we'll be getting another icebreaker with one of these mapping systems on it. And we go, and we do that, we've now mapped something like 420,000 square kilometers. That's Barrow, Alaska, the very straits here. And you see we've gone as high, that's in our pole up here. So all of this will be extended through a continental shelf up here. So the 200 nautical mile ends something like here. So we get a huge, up to 600-700 mile extension that again we can protect from other people exploiting. So very, very important. And all the dark stuff is the stuff we map. Again, each one has the great ice through the area. And again, every time we go out, that was the before map, and in this case, the aftermath with a huge seamount, 11,000 feet high, that we didn't know was there. And there are thousands and thousands of these seamounts that we don't know that are there. This one we named after the ship. These mapping systems also give us an amazing view of our maritime heritage. This is some survey work we did off the D-Day beaches. These are the Mulberry harbors, these artificial harbors that we built. You can see them here to support the invasion fleet. And the Navy was very interested in what their condition was. So you can see that this was one of when they ran out of caissons, they used old ships called block ships. 2 weeks after the Mulberry harbors were put in on Omaha Beach, there was a huge storm that destroyed the caissons, but by that time the Allies had actually taken harbors, that they didn't need the artificial harbor anymore. This is one of those block ships that was lifted up and smashed down during the storm. It's really quite remarkable and very moving. And we now get just these remarkable acoustic pictures. This would have taken weeks and weeks and weeks if we could have pieced together photographs of this vessel. But in a couple of passes with the sonar system, we can now get that kind of view. This is actually a wreck in the Port of London. It's a very special wreck. It's loaded with TNT. You see it's breaking apart. It's been there since the Second World War. We just don't know what to do with it. So they survey it every year to watch it fall apart, but they just don't know. So, I just don't want to be on the last survey. So the initial focus of all these systems was mapping the seafloor. But what's happened in the last few years has been a real change, and that's that we now can start looking in the water column, use the same systems to map in the water column. And our first effort was actually looking at fisheries, and now so again, the fisheries people always use sonars too, but they use just the same beam sonar. But now we can get this whole picture of what the schools are doing, whether they're avoiding the vessels or not. We can, well, this is more a visualization exercise than a mapping exercise, but it's the same kind of tools we use to actually, colleagues of ours, not our colleagues put tags on whales. And then those tags are recovered, and we recreate, we have a visualization lab, what those whales are doing. And so nobody's really known what the whales do underwater. And so this is actually a case where 2 whales were tagged for the first time. Every time they come to the surface, these spirals that set up, that's not the overview of that. These spirals are a really remarkable behavior when they're creating a bubble net. They have a bunch of prey and they go down spiral and blow in bubbles and trap the fish, and they come up to the surface with the tail and slap the tail and they stun the fish and they come up and feed. But here you see, this was the exciting thing. 2 whales were tagged for the first time, and one was a male and one was a female. They wanted to know how they collaborated in terms of feeding. And they found out. And it turns out that one of them did all the work, and the other one mooched. So I'll leave it to you to figure out which way that was doing the mooching. So most of that effort in the water column was really focused on the fisheries. And then we had this was about February of 2010, the first deepwater systems that allowed us to look in the water column. And we were coming on the test trip with the sonar system in San Francisco, and we saw this remarkable plume of gas, 1 mile high, coming from 2,000 or 6,000 feet up to 1,800 feet or so in the water column. And it makes sense. Gas is actually a wonderful target for sonar. It resonates very nicely. But we just didn't realize that these systems have this power to see that it's a standard in areas where there's oil and gas. There are lots of natural seeps of gas. So it wasn't surprising that it was there off California, but we were really surprised when we built the tools to visualize this. Well, this happened just a few months before Deepwater Horizon. And when that happened, we were asked to come in and actually start using this tool. And we did a lot of the development of tools to see if we could trace the deep plume of oil that was coming out of the wellhead. And particularly asked to come in when they finally capped the well. It took many, many months to cap the well, many attempts, and they finally in July were able to come up with what they call the 3-cap stack. And I had a 3 times a day report to the Secretary of Energy on the progress of our mapping. And he called and he said they're about to cap it, and they're worried that the cap actually works and it seals off the well. That inside the well, in the formation, there might be a breach, and it may blow out the side and come up through the formation. And if that happens, there's no stopping it. And he said, can you guarantee that if we put that cap on, because the first thing that's going to happen is gas is going to start coming up before the oil. And they can stop it if they detect that gas coming out. Can you guarantee that you'll see the gas? And boy, that's the greatest question I ever had. I brought all the smart guys in the lab together. We all thought, we said yes. Oil we can never guarantee we could see, but gas we could see. And they did it, and we came over it, and what did we see? This is gas coming right out of this is the capped well. And we reported right back to them, and BP responded, oh, I said, those guys don't know what they're doing. And went through 16, almost 24 hours of back and forth until we demonstrated that we actually were seeing gas come out, and they acknowledged as it was. And then had to send remotely operated vehicles with cameras down and determined that that's all it was. It was not the formation at all. It was just a seal on the cap itself, a little scratch in the flange, a little flange. And it was nothing serious at all. They kept the cameras on it for the next 3 months just to make sure it never got any worse. But that just a few moments a second leads to a spectacular target like that. That's how sensitive the sonar is to the gas levels. And so it became this is a tool that's being used by the oil and gas companies now for that kind of exploration and hazard detection all the time now. As I said, there's lots of natural seeps. We finally brought one of the multi-beam sonars into the Gulf of Mexico, and now started mapping all around where there's just thousands of seeps coming out, all natural. And what we're trying to do now is not just understand where they are and how much gas they're putting out, because that's methane. It's a very powerful greenhouse gas. And this source of methane is not really accounted for in models that look at ocean acidification, or if some of it actually reaches the atmosphere in the atmospheric models too. So we're trying to globally find where that is. And so we're trying to be quantitative, so we need what we call ground truth. Because, the sonar is a very remote way to measure things. So we're trying to figure out ways to calibrate the sonar so we can actually look at the sonar signal and say how much gas is coming out. But to do it, we actually have to do some tests. So we come down there and we can actually pinpoint quite nicely where the bubbles are coming out. We send a little remote operated vehicle, and we have to see the bubbles coming up yet again. So a little thing like that creates this big acoustic target like that. But then we go and we kind of look at their size. We see the little ice crystals forming, ice over here, something we call flat rate or high gas hydrate. All these little bubbles, so we look at their size. And then we develop a way to actually start capturing them on camera, measuring their size, measuring how fast they were, once we know their size, we then can use the acoustics to measure the flux. So that's kind of ongoing research. So the final thing I want to talk about is yet another application of mapping, and this is looking at mapping, using mapping as a tool for really understanding climate change. It's kind of a big jump. How does mapping the seafloor tell us about climate change? But it really does in places where there are glaciers. And it's also a chance for me to show some of the most beautiful pictures of the most beautiful place I've ever been, which was just it was last year. Yeah, last year. The northern part of Greenland, I'll show you, it's something called Petermann Glacier, Petermann Fjord. And so this is, I mentioned that the ice in the Arctic that we go through on the icebreaker is receding, and that's terrible. It changes everything. There's feedback mechanisms. Let's say there's less ice cover, so the ocean warms up more because the sun isn't reflecting off the ice and it accelerates cooling along. But that melting ice doesn't change sea level because that ice is already in the water, so it's displaced that water already. But if you melt glaciers on land, like Greenland ice cap, that raises sea level. And if the entire Greenland ice cap would melt, it would raise sea level by about 22 feet or so, 7 meters. And that's really serious. That would inundate millions of people in many places. And what's been happening over the years is that the Greenland ice sheet has been really, really melting very, very quickly. I'm trying to understand why. And one of the reasons that's associated, we don't fully understand the mechanisms, is that many years ago, almost all of the big fjords where the glacier would come out to the ocean had floating ice shelves. So ice that would then lift off the seafloor and float out. And what's happened over the years is most of those ice shelves have disappeared. And those acted as a buckets to stop the glacier from actually getting in contact with the seawater and melting quickly. And so we think this is part of it. So we're trying to understand one of the few floating ice shelves left is in this place, Petermann Fjord. I should say that's about 3,000 feet high. It's amazing. And this is where it is. It's pretty far north. Not easy to get to, believe me. And we had to fight our way with an icebreaker all the way through the Marion Strait up here. But we did. And you can see us, we left from Greenland, it's Air Force Base. And that's Petermann Glacier up here. And you can see the floating ice shelf is here, the actual Greenland ice cap is here. And here's a picture with the floating ice cap. And you see pieces of this break off every once in a while. In 2010, a huge piece, 4 times the size of Manhattan, broke off. In 2012, another piece broke off. So this one is receding too. But we're trying to capture and understand the processes here to understand it. Here you can see this was 2010. That's the piece that broke off of the floating ice sheet. There's a 2012 piece. And by the time we got there in 2015, it moved forward each year a little. But even our year, another piece broke off. Why didn't we? They're actually very fortunate because this was plugged up with ice, but a piece broke off and it kind of plowed a path through it and let us come back in with the icebreaker. And so there we are. You see, it's not so easy to move. It's a Swedish icebreaker called UNH. That's a lot more comfortable than the US one. It has a couple of saunas, actually 3 saunas, a bar, 2 bars. The US is another picture. And so you can see this gets the idea where it is. And that's the piece of the iceberg. That's the shelf up there that had broken off and plowed its way through to let us get in there. And so this was a remarkable program. Actually, you saw 60 Minutes about 2 weeks ago, 2 Sundays ago. I had a whole section about this. And we had people drilling on the ice. We had people making measurements in the water, people running around on land. You can see old stands of sea level, so we understand what sea level is. But our job was to map the seafloor. And what we were doing in terms of mapping the seafloor is turning this picture, this is what we knew of the seafloor before we got there, into this picture of the seafloor. Again, there's unbelievable detail, but recorded on that seafloor is the history of the glacier. Moving back and forward, and for those people who study that, you can actually see the streamline, see where the glacier came, where it stopped, and they take samples and they date it, and you can actually put together the entire history of the movement of the glacier back and forth and start understanding the processes So just one more application, kind of a real fun side of what we do, and of course you got the back of this vessel, the open, you see that back of the vessel sits really just that far up, and that air could easily come up there, and you'll see that's on the ship. They look cute, but believe me, there were many people with guns standing there, but fortunately decided to shoot at them and move on to stop there. Okay, so let me just try to sum this all up, and hopefully I've demonstrated that we really have the tools to now map our planet at a scale that we can understand what's going on. Let's look at how much of it has been mapped. Here's a plot that shows all of this multi-beam sonar mapping that's been done in the world, at least that we know about. And when you look at it at this scale, it looks pretty good. But let's zoom in to a place here that looks like it's completely covered. And if I zoom in there, that's what that really looks like. And if I zoom in again, you can see even that it's very, very sparse. The bottom line is only 11% of the ocean has been mapped. It's 11%. What would it take to map the rest? Well, what I'm going to do is I'm going to forget about the shallow water. Because remember I said that sonar is a big swath like that? So when you get in shallow water, I mean, 30 feet of water, I'm only going to map 300 feet at a time. That's really hard to do. That will come. There are other ways we can actually use satellites and planes and LiDAR, lasers that can do that kind of stuff. So I'm going to start 150 meters or deeper. And basically, to map the ocean, 150 meters deep, the whole world ocean, using 4 times the water depth as a swath, and about 10 knots, 10 miles per hour for the vessel. It would take about 65,000 days. The vessel costs $45,000, $50,000 a day. It would cost $3 billion. You say, oh my God, we'll never do it. Who in the world is going to spend $3 billion to map a planet? Well, we'll do it all the time. Moon is mapped to 100 meter, 300 foot resolution entirely. Every moon mission costs about $600 million. That's not $3 billion. Mars is mapped everywhere to 60 feet resolution, and in many places, it's mapped to 3-foot resolution. It's mapped to the resolution of the photographs we saw. And what's a Mars mission cost? $2 to $3 billion. And Earth, we look at you back there. If I go zoom in to the same level, 90% of our planet is mapped to that resolution. So I ask a question: why? I mean, it's an astronaut. I love space. I love all this exploration. Why are we so willing? How many Mars missions have we had? Why are we so willing to spend $3 billion to map Mars when we won't spend the same amount to map our own planet? And people say, well, it's easier because there's no water in the way. Well, I just showed you for the same amount of money. All it does is it just takes a fiscal willingness. It's not a technological challenge. So I'll let you answer the question. I don't know. I've been trying to get an answer to that for a while. We can do it. I showed you. At a resolution of about easily the whole ocean of about 300 feet resolution. But we have ways, as I showed you, to send the vehicle down with the sonars. I can get it down to the 3-foot resolution if I want. That's going to take a little longer with autonomous vehicles and robots. So we can do it. And so I just leave you with the idea that there's so much more to explore, and it's right here at home. And usually you end up with the thing that says the end, but I think in terms of ocean exploration, it's really just the beginning. So I thank you, and I'm happy to answer questions.
It reminded me of something that I'm wondering if people in this room know about. It's related, sort of. In October this fall, a group called the Arctic Council. Are you familiar?
Well, I'm very familiar.
Yeah, they're going to be meeting here in Portland.
They are. I just know that.
Yes.
Okay.
And I have an online news blog I came across this information in the city report accidentally, or I've written about it on my blog. But anyway, Secretary of State John Kerry, he's gonna be here.
Right, Admiral Pack will be, because he's the chair of the
Yeah, the
Arctic
whole
Council.
crew is gonna be
And Fran
here.
Ulmer.
Huh?
And Fran Ulmer will be here. She is the chair of
Yeah,
something called the Arctic Research Commission, which I just got appointed to. So
oh, really? Yeah, they're all gonna be here in October.
I didn't know
The
that.
meetings start in September. They've been planning this for 2 years. Excuse me, and they're gonna be staying at the Westin Hotel. We have 290, oh, well, we don't want to know about that. But
But
anyway,
are the meetings that start in September going to be here too, or?
I believe so.
Because I know there's something going on in September, and it's going to be right over at sea, that is, they call it a ministerial summit in preparation for the Arctic Council.
Yeah.
And I thought that was in Washington, so they'll probably move from there to here.
Oh, well, maybe there's something, but according to what I was told, all of these meetings, including the September meeting, in Portland, and I was also told the outskirts of Portland. I don't know how far.
That must be Durham, New Hampshire.
And there are going to be, I think it's 26 countries here represented.
Yeah, the Arctic Council has, there are 5 Arctic coastal nations, and then there are 3 others that are called Arctic states. But then there are a number of countries that have observer status on the Arctic Council.
Yeah.
So that's a great honor. That's wonderful.
It is, and it's very exciting for Portland because I think Angus King is involved in this.
Well, Angus King has also been the leader with Senator Murkowski from Alaska. Is it
Yeah.
Murkowski? Is that?
I think
Murkowski
they
from
met in
Alaska.
Alaska last year.
Right, and the Arctic Council did meet, and they started what they call the Arctic Caucus in Congress. So the 2 of them are basically leading. Is it?
And also, what's the other thing? Something else, maybe I'll think of it.
Okay, I'll go to this, and we'll come back.
Anyways, I think.
That's great. I didn't know that.
AIMSCIP, which is our container company, they are expecting that this will open up trade routes for the Port of Portland to more global, venues, through AIMSCIP, our container company. And so it's very important for Portland to host this, but also the potential for the future for the shipping in the Port of Portland is huge.
Great.
How is sea mapping used in archaeological work in, say, the Mediterranean and the Black Sea?
Yeah, it's constantly used there. Same techniques. I've been a number of times. Ballard has been one really used Bob Ballard. And so he had his ship called the Nautilus with one of these sonar systems on board. And usually what you do is it depends, the resolution you see of an object on the bottom is a function of how deep it is. And so if it's very deep, you're not going to be able from the surface to see something, but you might see hints of it. So you'll map from the surface first and then send down remotely operated vehicles. But it's exactly these techniques that are used now for locating things. And then still at the end, they'll still come down and start doing the photo mosaics to really get the highly accurate parts. But what the nice thing about the mapping is it gives you a photo doesn't give you a 3-dimensional picture, but the mapping part does. So if you remember that wreck I showed you, you really see it in 3 dimensions. You can make all the measurements, quantitative measurements. So the days of the archaeologists having to sit there with strings and a grid are over. They can just use the sonar mapping and get that quantitative measurement of the wreck. So it's a very critical.
Can you talk a little bit for someone who I don't know much about this, but you talk about using the sound. Does that have an impact on the marine life at all? Or
Yes,
how-
that's a great and important question, and it's something we always are concerned about. There's no question that certainly marine mammals, toothed whales, particularly porpoises, they use same type of system, an acoustic system, sonar system to communicate, and so they clearly can hear the sound. We have some very good ideas about the frequency range over which they're sensitive in, and most of our sonars, the shallow water sonars, operate higher frequency than they can hear. Some of the deep water ones, the big ones, operate at frequencies that are in their hearing range, but the sounds are so short, the pulses we put out are so short, and I said it makes a big fan, it covers a wide area, but it's absolutely narrow. that statistically the odds of marine mammal intersecting that are very, very small. But we have to go through a whole permitting process to use those lower frequency ones. That's for that kind of system. The systems that the oil companies use to explore for oil and gas, these called seismic systems, are much, much stronger, and the Navy sonars that go up for searching are much more powerful. They I think, have shown to have an impact. And so now to use that, it's a very, very strict permitting process, and there are all kinds of mitigation procedures. Every vessel we go on has to have marine mammal observers, so if we see a marine mammal, we shut everything down. So we try very hard to not have any impact. But it's still something that's a very hot topic and being discussed all the time.
Related to what you talked about with the different resolutions, what is the range of resolutions you can get from, say, someone like a Captive Bay versus the Mariana Trench in those depths? And what are the frequency ranges used?
So everything, one of the things about acoustics is everything is scalable. So the higher the frequency, the shorter the range it goes, the higher the resolution. And so in shallow water here, we can use frequencies like 200 kilohertz, 300 kilohertz, and those will go kind of 600-700 feet water depth. If you want to go to the Mariana Trench, which is, anybody know how deep that is? 33, 34,000, 35,000 feet. So I don't want to use 11,000. We haven't mapped it exactly. It's actually 10,996 feet. So about 34,000 feet. So to do that, you have to bring it to lower frequency. And those frequencies are typically 12 kilohertz, 12,000 cycles per second. And those will travel through any depth of the ocean. And those are the frequencies that are, and that's why whales can operate at those frequencies too, because they travel very far. Yes.
So you were talking about what a big job it is to map the whole of the ocean with these multi-beam sonars.
We're going to call multi echo sounds.
Oh, sorry. So I'm wondering, like, do universities own them, and oil companies, and countries own them, and navies own them, and so actually it's not like one person has to raise all that money. There's like,
well, that's a great
there's like
question.
hundreds of people out there.
Yeah, well, I should say these deepwater systems are over $1 million each. They're not inexpensive. Even the shallow water ones, which are only about this big, and mount on a small vessel. We have a vessel. We have a vessel that's probably worth a couple of $1,000, but it has probably $500,000 worth of echo sounding equipment on it. So even the small ones are $300,000, $400,000. They're very complicated pieces of equipment, but there are hundreds and hundreds of them. And you're absolutely right. What we're trying to do, there was something 3 years ago that I was involved called the Galway Accord. So it was a collaboration between the EU, Canada, and the US. We signed an agreement that we're all going to work together to try to map the North Atlantic. So each country, whether it's an academic vessel, not the industry has other motivations, but academic vessels, government vessels, will try when they have an opportunity to fill a gap. And it's one of those that's happening right now. There's a trend going on between St. John of Newfoundland and Tromsø, Norway, on the Canadian ships. Each year that they get confused. So, but that's really slow and piecemeal. I want to just go through it. It'll take, those numbers represent 200 ship years. So if you 200 ships in 1 year, or 20 ships in 10 years, or at the meeting a month ago, I proposed a giant barge that could be towed around the duty faster. There are ways to do it. Just some of these have to say it's worth it. And in all honesty, there was this big meeting a month ago, a month or two ago, and there's an article, there was one, and will be another one, the Economist all about this. And there is growing momentum. I had a call from the oceanographer for the Navy about this, how do we go about doing this? So, I think people, and the Nippon Foundation, which is a very, very wealthy Japanese foundation, made a pledge that they want to see the ocean map by 2030. So they actually have the money to do it. They just take it. I don't know if they meant it that way.
How many countries in which countries actually have
Yeah, I could say it started strictly in the U.S. military thing, And then there was so the U.S. military was developing this all kinds of and that was in the late 70s. And by the early 80s, it became commercially available Regis company. It was really a Danish company. So I think most of the developed countries have both in the academic venue and in the industry has it. And so they're looking at that why. The non-developing countries will find some arrangement with, like when we go out to the Pacific, we'll map for Vanuatu, places like that while we're out there.
The bubbling is so prevalent on the west coast, that was methane and bubbling out through the cracks and the frost. So oil moving out.
Yeah, absolutely, yeah, oh yeah, with each one of those seeps is often oil bombs, and if any of you lived in Southern California, or Waterway, places like Long Beach, there are always oil bombs washing onto the Santa Barbara, the plastic place, and they're not from oil wells, they're natural seeps that are coming up, and you walk along the beach and you end up with tar on it, and that's natural oil seeping.
That's probably been going on for millions of years. Right?
Absolutely.
Does the ecosystem evolve in any way to take care of that?
That's a great question, yes. And what has evolved, particularly in places like the Gulf of Mexico, which was those places, and that's why, as horrible as the Deepwater Horizon still was, there is an ecosystem of microorganisms, microbes, that have learned to basically eat the oil, and they degraded it very, very quickly. And that's why they were not as long-term effective as they could have been. And that's why I'm so scared of something like that happens in the Arctic, where that ecosystem isn't. And then we're really, really in trouble. Don't count on us always. Let's prevent this going another thing. Yeah.
Can you measure ocean currents with this technology based on density and salinity?
Yeah, that's a great question. There are acoustic tools that are used to measure ocean currents. They're called ADCPs, acoustic Doppler current profilers. And so they use sound to bounce off something like a layer and look for a Doppler shift because the vessel or the current is moving relative to the layer. And so it's not exactly this process, although I have to tell you, this is a secret now. We're actually in the Arctic, we've been seeing in our multi-beam sonar records oceanographic density differences in the water itself. And we're actually looking at the exchange of the Arctic and Atlantic water. So maybe even these systems, not measuring the current speed, but actually looking at the interfaces. But there are acoustic techniques to measure current speed. Somebody else?
Yeah, time for one more question. That's all right.
So the oil and gas industry has the ability to do this type of mapping. And the government, as they're selling leases offshore for resource exploitation, how much of those areas is mapped? Like, do the oil companies know more than the government knows about what the plots that they're selling?
Yeah, okay, so that's a really good question. I'm not fully an expert on this. The oil companies certainly don't invest $3 billion without having some good idea about what's there. But as far as I know, when the oil companies do that, they have to provide that information to what used to be called MMS, Minerals Management Service, now DOEM. It's not made public. That's something we're very frustrated about, because there is more of this data available, which is not made public. But I think the government, the regulatory agency gets access, so they can see it.
Great. So thank you. Join me again. More lectures in the series coming up, and for those of you who are members of GMRI, please consider giving us a donation. We'd love to have your support. We need support from people like you, people like John, and bringing great people like Larry here to tell us about all the awesome stuff that's happening out here, and for us to learn more and explore about the Gulf of Maine. So thanks very much for coming tonight. Thank you.